Hello, everybody, and welcome to this SimScale structural webinar. My name is David Short. I'm the product manager of the structural analysis components here at SimScale, and I'm very excited today. I'm joined by one of our favorite customers. I know we're not supposed to have favorites, but there it is. That's Dr. Alessandro Scafato from ANYbotics, and we're going to be looking at some of the work that they're doing with their amazing robots and how they bring simulation into that. So, Alessandro, if you wouldn't mind introducing yourselves in a few words.
Yes. Hello, I'm Alessandro Scafato. I'm a team lead of verification engineering at ANYbotics. I have former physicist and now turned engineer, and I'm dedicated all my life in verifying verifying products in the high-tech industry. And now I am, let's say, leading a team to verify complex mechatronic quadruped robots. So.
Awesome. Thank you so much. So let's get into it. Today, I'll give a bit of an introduction into SimScale, particularly around advanced structural analysis, which is really where SimScale shines, and it is what Alessandro does day to day and his team do with the SimScale platform. So I'll give a quick introduction there. I'll also introduce you to how we integrate with SolidWorks. As ANYbotics are SolidWorks customers, and we have many SolidWorks customers, we've developed a specific workflow for integrating CAD changes in SolidWorks into the SimScale platform as well. And then we'll get into the bit you're all here for, the actual customer case study, and learning how ANYbotics use simulation day to day. After that, we'll have a short Q&A. So if you do have any questions, please do write them into the questions panel in the GoToWebinar dialogue, and then we'll do our best to answer all of those at the end of the presentation. So on to SimScale. SimScale is a purely web-based platform, right? And that comes with a couple of massive advantages. It means it's accessible from anywhere at any time. And because it's 100% cloud native, that means all simulations that are run, they're run in the cloud. It means that it can be accessed at any scale. So if you bring in a small model, we'll run it on a smaller machine. If you bring in a large model requiring a large mesh, it will run on a large machine. Now, the scalability doesn't stop there. It is also about running simulations in parallel. Okay, so in parallel, you can run as many simulations as you like, and this brings huge advantages for advanced structural analysis, right? And SimScale really does make advanced structural analysis truly accessible, specifically through this concept that you can be running transient analysis, dynamic and non-linear analyses, and you can be running them all in parallel. So you've got multiple design candidates, you want to run them all at the same time, not wait for one simulation to finish before you start the next. So it allows you to explore a huge amount of design space in a short amount of time with advanced analysis types. Some key features that I really want to highlight is the fact that we include nonlinear, dynamic, and thermomechanical capabilities all under a single standard license. So there's no tiered pricing. You come to SimScale and you get all of the structural analysis capabilities. I also want to highlight the fact that we have really the world's best engineering support for simulation, and that is directly in the platform itself. So our ethos here is to make sure we're helping you with the problems that you have or answering your questions directly when you need or directly when these questions come up. So there's live support in the platform itself. And for advanced structural analysis, support is going to be crucial, right? For many types of applications, having that expert tool knowledge at your fingertips and having the people there to help you out with those problems is a real game changer. Now, why do we simulate? I'm sure the majority of the people on the call know all about this. I'm sure you're using simulation day to day in your product development strategies, but a few quick ideas. We want to make sure that we're doing design space exploration at low cost, enabling innovation through through simulation itself. So sometimes simulating it will surprise you. It can spark new ideas, and it can really point you in the right direction of travel within your design space exploration. You also want to make sure you get those design insights, those crucial design insights, before we get to physical prototyping. And we'll hear more about this from Alessandro a little bit later on. But it really means that you can focus on your high potential ideas without wasting energy or physical resources for making models and testing them on poor design concepts in the first place. The final thing about validation, we want to make sure we can replicate the physical testing exercises that you actually do on your physical products. Now, physical experimentation is fantastic, but you can only have so many strain gauges. You can only have so many accelerometers, right? If you have a problem in your physical testing, you want to know point-wise exactly what is happening at every point in the model, and that is what simulation can bring. A couple of examples of the type of advanced structural analysis that we do here at SimScale. So here I'm going to focus on the nonlinear analyses. So that's nonlinear contact analysis, for example, for these snap fits, clips, and plugs that you see on the left, but also for rotor and shaft interactions, where you might have an interference fit or a frictional fit, and you want to make sure that you size that appropriately and understand the stresses on the model that are experienced just due to that interference fitting. So normally done with a thermal interference fit, you cool down the shaft, you pop it into the rotor, and then you let it warm up again. What kind of stresses do you actually develop in the rotor itself? Now that's critical information, and you can run many simulations in parallel to understand what type of interference is going to cause which effect on your design. Again, with bolted connections, so in thermal analysis, thermal shock, you may have, for example, a globe valve there under pressure loading, under thermal loading, and it's also bolted together. So there's quite a lot of complexity into modeling those. You need to make sure you have nonlinear contacts between your flanges. You need to apply the bolt preload as an initial step in your simulations, and SimScale has automated workflows for that. Moving on to dynamics. So a lot of the work our customers do are around dynamics and vibration in particular. So obviously vibration is critical, particularly in the electric vehicle industry, in robotics, in many other industries as well. And we provide the resources that you need and the workflows to make sure that you're efficiently simulating your vibration testing and mitigating any risks upstream. So we've got vibration analysis. We've also got dynamic impact and shock analysis using transient dynamics. And we also do go into some rotor dynamics effects in modal analysis, where you want to understand where are my critical speeds for my rotating parts. For plotting Campbell diagrams, you can then find your critical speed, for example, with the electric motor, rotor and shaft image you can see over on the right hand side. So on to SolidWorks integration and how our customers can use a specific plugin for SolidWorks to interconnect your CAD world into the simulation world and ensure CAD associativity. So I've got a little video that I'll play for you now around a demo of this strategy, so then you can get a full insight into how our customers actually integrate these two different softwares.
So here we are in SolidWorks. Let's see how SolidWorks users can benefit from the new SimScale plugin to perform rapid simulation-driven design changes. Here we have an EV battery module. The assembly is made up of over 100 parts, and we need to perform a vibration analysis within SimScale. We'll perform modal analysis and we'll check for the risk of resonance between the critical frequencies of 0 and 200 Hertz, as stipulated by many international standards, including the UN 38.3 testing standard. With a couple of clicks, we can create a new SimScale project and export the SolidWorks model directly to SimScale. Open up SimScale and you'll find the new project with the SolidWorks CAD already imported. Here we can then create a new study. We'll go with a frequency analysis, which is a modal analysis, and we'll skip the setup for now and take a look at the results. Looking at the first mode, we can see that it's at about 240 Hertz. Now this is a little bit too close for comfort to that physical test range of 0 to 200 Hertz. So what we want to do is maximize this lowest energy mode away from the test range. And one way we can think about, or one thing we can think about doing, is changing the bracket design and stiffening up those brackets. So let's jump back to SolidWorks. We can now edit the bracket before pushing the new design back to SimScale to be run with the same simulation setup. Okay, so now I'm happy with my bracket. Let's update the assembly. Now I can export this new design to the same SimScale project using the SimScale plugin. I can give the geometry a new name and export. With the SimScale plugin, we guarantee CAD associativity, which means we can use exactly the same simulation and simply change the geometry to the new design, and all the settings remain. So then there's no need for extra setup, and we can simply run the new simulation. Taking a look at the results, we can see that we have pushed the first eigenmode well away from the physical test range, which means that we have mitigated the risk of resonance during physical testing. So there we go. We've now seen how SolidWorks design changes can be seamlessly integrated with the SimScale platform.
Okay, fantastic. So now you've had a taster of how SolidWorks and SimScale can be integrated together. I've introduced you to some of the advanced structural analysis that our customers typically do. And now it's time to actually understand what the ANYbotics team have been getting up to with the SimScale platform. So I'll hand over to Alessandro.
Thank you.
Bear with me 1 second. There you are. Now you're the presenter.
Perfect. And I will just present my screen. And here I am. So what I'm going to talk to you about is essentially how we verify our robot and how simulations is embedded in our design process at ANYbotics. So a quick introduction on what we do. If you don't know, we are a company that designs and manufactures as well quadruped robots for industrial inspection. Okay, so the concept is rather simple. You have a robot that is deployed in an industrial environment, and you can see from this second image in this very colorful image over here, we map the environment, and then every day the robot several times a day wakes up and performs a mission. And in this mission, it can read cages, it can take thermal measurements or acoustic measurements, and then sends its findings back to the system of our clients. Okay. The company started, well, the work on quadruped robots started in 2009 at ETH Zurich, and only in 2016 we seen ANYbotics come and become a company, right? I joined roughly before the release of Animal C in 2020, and since then we have released Animal D, which is our first certified industrial grade inspection solution, and Animal X, which is its X-proof counterpart. put it easy. And so we serve a range of industries, and our design, let's say our design strategy is embedded in this concept. We are targeting these industries and we verify our robot against these environments. But if you look at just these 5 images, you can already imagine just how broad is the landscape of places and challenges that this robot faces, right? We have stairs, we have rough terrain with rocks and sometimes nature grass. We can have slippery surfaces or gratings which are see-through and all sorts of things. If you imagine that this robot is autonomous and walks around this environment freely, then you add up a virtually infinite set of challenges that this robot can face during its lifetime, right? So at ANYbotics, we have a verification engineering group that is dedicated especially to verify our design against these occurrences, right? Normally, in my career, at least, I experienced a lot of industries, and you would have a testing and a simulation, and these testing and simulation are essentially 2 separate entities. At ANYbotics, this is in one entity. We perform both things, and this is because, first of all, yes, testing is heavy in terms of how much time and money it consumes. You have to procure things and set up the experiment and then run it and then do it again if something goes off. And on average, simulation is used as a cheaper counterpart for testing, but we don't like that, okay? We believe that both of these 2 men in the slides are essentially wrong. You don't believe everything that you see, and you don't believe everything that is explained by math and theory. What you start believing is when what you see and what you predict tell the same story, okay, tell the same narrative, are in agreement. So our group is dedicated to create this agreement and provide a fact-based, actionable feedback to designers, so an indication on where to go, not just a pass-fail scenario, right? We have a philosophy behind what we do, and essentially what we want is that for every bit of design, we want to predict and experience what we predict and explain what we experienced, and each of these 3 pillars support each other towards a direction, right? And here we encounter a bias, and the average bias is a life bias, right? Is the bias that if you buy the best thing, you're gonna have the best outcome, right? This is not entirely true. In reality, yes, a bad tool lead to bad results, but a good tool is not enough. You want to have, first of all, a robust process in the background that sustains your convictions, your findings, but you also want to have very knowledgeable people that understand the depths and the background of what is happening. They know what limitations you're applying to a test or to a simulation, and are able to explain why the test or why the simulation is behaving in a certain way, right? So let's start with the process. Here you have 2 processes. They probably don't look like any real process, and this is not the point to make it real. The point is to convey a message, right? Traditionally, you would hire a designer, and this designer is a talented person. It has experience and prior knowledge, and will run through concepts to come up with a design, maybe with a Proncon list or some other criteria, and then you will start designing and using either pen and paper calculations or FEM simulations as a sanity check to their design. Right? Then you arrive to prototype and testing, and the testing will give you the final answer of whether the solution is good or not. Now, if you're dealing with a technology that is well known, that has a lot of prior knowledge, you will probably know what's going wrong if the testing is giving you bad results, and then you can go jump back into the design phase again. But in high tech, and especially whenever you perform innovation, you are stumbling across this other loop in which you don't know what's going on. Well, if you knew what was going on, then it would have already happened. Somebody would have already done it. So this is a nature of innovation, is in the nature of high tech. It's nobody's fault that this happens. But when this happens, you have opinions, right? You try harder to make your design work, and this adds up to an expense, adds up to stress with disagreement and arguments. Other people may have different opinions, may have different experiences, right? And it's a very it's a very dreadful loop to be caught in, right? So our process tries to avoid that loop. And what we do is that we implement simulation and testing very, very early stage of the process. In concept stage, you have very rough designs that are cheaply manufactured. You can do very easy experiments that can be easily verified via FEM, and therefore you can already start building up a set of tools, whether it's simulation or experiments, or both, mostly both, that essentially are already in agreement of what is the physics behind it, what are the problems behind the concept. And with all of that, you're already gathering knowledge of your system, and you're already gathering knowledge of your concept. You're getting to a point in which you are confident your concept is correct, but also the tools you're using to verify are there and are validated already. And when you enter the design phase, you can run simulations, you can run your models, your simulations very fast throughout the entire design process. And you enter a loop in which you constantly simulate what you're doing as you are designing it. This is a fast iteration loop. You will do it many times. You can run hundreds of simulations over a single part. But at the end, you have a high confidence of what you're doing. When you prototype and test it, essentially you again get into that point in which the test may be agreeing with your design and with your prediction of the design, but it may disagree with it. But at this point, the problem is not what's going on, is how do I make my model agreeing once more with my design, with my test results. And this is a much easier problem to solve. It's a much more technical problem to solve. So once you solve this, you can re-enter the loop and reuse the same process to design again until everything is optimized. Your part is exactly how you want it to be. Of course, this is a lot of wishful thinking in this process, but we try to stick to this as much as possible, and it has great results, I have to admit. So we have certain requirements when it comes to simulations that stems exactly from that process. We need to be able to make a lot of simulations. Virtually every designer simulates in this company. We need to make a lot of iterations that are fast and are accurate, right? And we use this process for every aspect of the robot, which is electrical, thermodynamic, and mechanical. So you have fluid dynamics, you have thermodynamics, structural mechanics, you have a lot of physics in there that requires a lot of expertise and knowledge and requires a tool that is very, very adaptable. So when I joined the company, I was in charge of finding the correct tool to do this and to enable us to get to that stage and run that process the way we thought of it. And I chose SimScale, mostly because it was cloud-based. It had all the physics that I needed to be done. But most of all is because I found out that their customer service was excellent. And this is a great advantage for a small company, because as a small company, you cannot build all the expertise and all the knowledge of all this physics in-house immediately. It needs time, it needs effort, right? But because we had the support of SimScale people and customer service, we were able to do the things without having to develop all the knowledge ourselves, right? We could borrow the knowledge from them, and we did relentlessly, I would say. So yeah, we chose this. And aside from this, we had an added benefit, which was the model of SimScale allowed us to, first of all, save on infrastructure because we didn't have to buy computers for our FEM, but also be able to track how expensive our simulation costs were for each part. So how did we use SimScale? Well, we use SimScale for everything. We use it for detailed designs. You have here the typical example of a foot. The foot is probably one of the most, if not the most important component in a robot, because it's most exposed. It impacts the ground every time the robot takes a step. It is non-linear. It can be made of foam. It can have different shapes, different threads in it. It can be mounted in different with different mechanisms, and all of them need to be checked. We run over 500 iterations of a food design, and we are running even more because food design really never stops. It's such an important part that you will never stop developing, right? You always want it to be better. It's what interfaces the robot to the rest of the world mechanically, right? Then we have full systems, which the main example is a leg, right? And in full system analysis, we use multi-body, of course. And what we are trying to do is we are trying to really predict all the load cases that the robot might be affected by. So we try different shapes of the leg, different angles of loading, different magnitudes of loading as well, and try to expose every weakness in the structure that we might have overlooked. Right. We also run fatigue analysis on this to as a sanity check to see if the lifetime of the robot can be achieved. Then we have cooling, because everything that has electronics needs to have cooling. And in this case, this is a airflow solution with the 2 fans. But what we did is essentially try all sorts of interface between the chips and the structures, different types of heat sinking, different types of fans, different ways of putting them in series or in parallel or arranging them differently, until we were happy with the solution we found. And last but not least, we have also very specific requirements that sometimes come from certification or from very specific, encounters that the robot might have in the field. Right? In this case, you see a simulation of an impact test. And this impact test is a very well-defined test that can be replicated. It's defined by a standard, right? So we needed certain components, many components of the robot, to pass this test for our EX-proof certification. And what we did is, instead of running the test over and over again in-house, we developed an FEM model, we validated against our tests, and then we used the FEM model to iterate our design until we were happy with it. So in this way, we optimized how much money and how much time we were investing in testing the design, instead of simply going for it every single time, right? So what this process got to us, right? And we have now 2 robots, 2 products. Actually, one is ANYD and one is ANYbotics. And ANYD is a regular waterproof, dustproof robot. It's not a simple thing, but is not an X-proof robot, right? And ANYbotics is our X-proof counterpart, right? If you don't know what X-proof means, it means that the robot must not ignite because of flames or explosion in its surrounding, right? And must not be the cause of flame or explosions to the environment. So the sparks and heat that is generated by the robot cannot ignite volatile gases, for example. When you design an X-proof product, the main risk is that you will need it, of course, stronger structures. You will have to comply with a lot of regulations and certification boundaries that are set on you. And of course, this has a risk of making everything bigger, heavier, and generally uglier, right? I think in this optimization process actually made sure that we could create an ANYbotics that has almost exactly the same dimension as ANYD, and almost exactly the same weight, which is, to me, is something that I still find hard to believe, because it's such a hard task to achieve, right? Yes, and unfortunately, we couldn't keep them the same color. But last but not least, I would like to add a note of appreciation from ANYbotics. I think SimScale, since we employed it in our company, was a very an excellent tool. It allowed us to achieve our FEM-aided design process without spending too much money, without being a weight on our shoulder, right? And the thing that we most appreciated was especially the customer service, because it provided an invaluable source of knowledge for us that really fast-tracked many topics in our FEM challenges, right? And the cloud-based approach was perfect for us because we didn't have to add infrastructure, which can be quite heavy for a startup. So thank you for listening. And I will give it back to you.
Oh, perfect. Thank you so much, Alessandro. That was fantastic and super interesting to number one, understand a little bit more about your sort of verification and engineering ethos and principles, but also the specific applications that you're running at scale in SimScale. So let me just take back control of the screen. Okay, there we are. So again, yeah, thank you so much, and particularly for highlighting some of the things that SimScale brings to the industry that you don't really find anywhere else, with the full cloud native solution plus the live in-platform support. I do actually have a couple of questions. I'll wait until some more questions come in from the audience as well. So we've already got some which are specific for me, I would say, about SimScale in general. But before we do that, I'd love to understand a little bit more about where you want to go next, right? With simulation, and the like. Do you think your process is now solidified, or do you want to go further with simulation?
Well, going forward is not. It's a no-brainer. You always go forward, right? You always want to improve and to make things better and faster. So now is well, we have established that the process is useful, that the process is there. What we want to achieve, especially with this team, verification team, is really establishing a standard for it and making sure that everything is really done thoroughly, and everybody is able to do it, even without the prior knowledge, even without the experience, right? So we are enablers of the company, right? And we want this process to be stronger, faster, and more effective. That's for sure.
So when you think about, so it feels like there was a lot of work up front, right? You had to get your process in place with the simulation, but now you've got to a point where you essentially have your models, and they'll require some, or they'll take some design iterations. You'll make some modifications, but then you've already got essentially your simulation process templated out, right? So I suppose someone coming into the company now, once you've got this established, it makes it quite easy to hire someone in, or to bring them into the design process quite easily. But how long did it take to get to that point?
Well, to get to that point, it took a full couple of years, I think.
Yeah.
It was not easy, and it's still, to be honest, yes, the templating and defining this basis for it and the process for it is important. But in a product like Animal, right, you have software changes affect hardware, right? And software and hardware constantly evolve in parallel. Right? So even with these things in place, we have to find now very fast way to transition these software changes into hardware, because every time you have a software change, you need to measure something. You need to measure, for example, ground reaction forces from the floor, because the robot now walks differently, right? You also have things like wear over time. So your shoes do this, right? You walk and your shoes wear out, and you maybe not feel it, but your feet feel differently, and your vibration increases, and all of that. And we need to track all of these effects. We need to refine everything to this point.
Do you loop that back into the simulation world? So say your effective, say the soles have worn out on your shoes, and then you loop that back in?
Yes, we have test benches for that that track the ground reaction forces over time as the leg stomps on the floor, right?
Yep.
And every change we make, we run through let's say, well, it's in development, this phase, but it definitely runs a routine of tests in which we gather data from the environment that the robot causes to the environment and intrinsic to the robot. So we rig the robot with sensors, right? And we use that data back into the simulation as load cases. So our load cases tend to be as realistic as possible.
Okay, cool. So it almost feels like you're moving towards a kind of digital twin kind of structure, right? That maybe can you know, I mean, that's where we want to go with SimScale as well, because we're cloud-based, right? It lends itself to automation, and it lends itself to things like digital twins. So the more that you can then feed back real-world data, either on the geometry or in the load cases, the more confidence you can have in terms of the lifetime of your product. So that's super cool. Let's just have a quick look at the questions coming in from the audience. So, can SimScale conduct topology optimization or generative design? Unfortunately not. So we haven't gone down that that route yet. So we're working with solid body meshing and traditional FEA for the time being. That's not to say we won't go down the topology optimization route, but we tend to stick to parametric optimization, right? So you've got your geometry, or you've got your 100 different design candidates, or you're doing that based on the simulation results, and then you can be running them using parametric optimization studies in simulation in SimScale. But no, you would need another software for topology optimization or generative design topics. Okay, do we have any more questions to come in from the audience? Anything specific for Alessandro? I'll wait a couple of minutes. So one thing I find difficult is to predict the load case. How does ANYmal manage this?
That is a question that is very recurrent and very interesting. The problem of animal is essentially that it behaves and walks like a person, right? So it encounters too many things to be able to predict, let's say, one fixed load case for your simulation, right? So what you do and what we do is we have a reference load case, okay? So we have a test facility. In this test facility, we know what is happening. Let's say walking up down the stairs or going through a catwalk, for example, with sensors, and we establish that as our baseline, right? We tune that condition to our industry. So we know the flooring, the general environment is tuned to what we believe is mostly what the robot is going to see in its lifetime. This is especially if you're doing fatigue, okay? Because fatigue is based on the normal execution of the robot. It's not an accident, let's put it like that. And then you do this for various situations, right? And you have you can do this. You can say, for example, we expect the robot to walk for that percentage of his lifetime on a surface, and from that percentage, he's going to do stairs, and from another percentage of his lifetime, he's going to do this, and you add up everything into a Miner's law, right? And run your fatigue test that way. But yes, this is an ongoing process, and it's effectively, my belief is that it's impossible to catch every single load case of such a machine, right? You would have to have a confined and let's say a secure environment for it to confidently say, hey, this is the load case that is gonna see. Was that answering the question?
No. For me, absolutely. That, I don't think we have live commentary, so we can't actually hear from Bingyin who asked that question. But Bingyin, please do let us know via email if you had any further questions there as well. Okay, we have one question regarding the speed of the simulations. Is this tool mostly orientated towards the design and testing of the robot hardware, or can it also be used in the design loop for the controller? Also, could it be used in applications with reinforcement learning? Now, that sounds more like a robotics question to me. Alessandra, if you wouldn't mind.
I can answer that. I mean, maybe you can tackle the SimScale capabilities side of it, but essentially, yes, you can. The difficulties of let's say benchmarking control loops in using an FEM tool is that you have to constantly measure the outcome of those and translate them into load cases, into mechanical load cases. And the difficulties we find with this is this. Well, first of all, we try to do this. We actually have a process for it. It's an unfortunate process because in let's say in hardware and software, there is no there is no automated link that can go from let's say developing a new control algorithm, measuring the forces applied to the robot, and then go back into a let's say an FEM model and a calculation. It's not automated, but it is done, and it has to be done because this sort of in a robot like ANYmot, control and let's say the locomotion of the robot and all the software side of it affects heavily our designs. The more graciously we walk, the more lightweight we can make our design. The less we have to worry about fatigue and this sort of things. So.
Okay, fantastic. And quickly regarding the speed of the simulations that Guillermo also asked. So it really depends on your mesh size. So as with all simulations, it's going to the compute resources required is going to depend on the number of nodes in your mesh. But the great thing is we have an unlimited number of machines at our disposal, and for larger mesh sizes, so going up to 5 million degrees of freedom or so, we're going to step up onto a 64-core machine and run it nice and optimally to make sure you get the best runtime out of your simulations. So that's automated behind the scenes, and we use a bit of AI to make the relevant choices for the compute resources based on the thousands of users that are running SimScale simulations. But that can also be manually controlled as well if you want full control over the type of resources you want to run your simulations on. Okay, fantastic. I think we're going to have to wrap it up there. So we've had a few questions there. We've had a couple of thank you notes as well, and we did answer Bingyin's question. So good job, Alessandro. So once again, thank you so much to all the attendees here. I hope you got some value out of the presentation and learned something. I know I certainly learned a lot from Alessandro's presentation, so I want to thank him as well massively for your contribution here. And yeah, we can leave it there and say goodbye to everybody.
Thank you very much.
Okay, bye everyone.